Inverters. What is the difference between this equipment and this one? This is the battery charger, and this is the inverter. This one, the input is AC, and the output DC. Okay, what is the other name of this element? Rectifier. Rectifier. The element that you have to charge your cell phone, you plug it on the outlet 120, and the output is 3 volts, 3.5 volts DC, no? To charge the cell phone. This is other rectifier, no? Yes or no?
Yes.
The alternator. The alternator produces DC power, and internally have a group of diodes to rectify the AC current, you remember? Into DC, the rectifier. Okay, the battery charger is a rectifier. And the marine battery charger is a sophisticated rectifier. The circuit board is a perfect circuit board, and the DC output signal is perfect. The DC output signal coming from the rectifier is exactly the same DC signal that you have in the battery when you read the voltage between positive and negative. It's not similar, it's exactly the same. For that reason, with a good battery charger, I can charge a battery, no? I can recharge the battery. It's clear? Oh, can I charge this battery with the charger of your cell phone?
No.
Yeah, you can, but you spend 27 days charging that battery, or 30 days, or 40 days, because how much amps produce your charger of your cell phone? It's 2 amps, 1 amp, no? And how much amps have this battery? 100 amps. You need 100 days, no? To charge this battery. Yeah, you can, but you spend a lot of time. Can I charge this battery 100 amps with a battery charger 10 amps? Yeah. Yes, but I need
11 hours.
11 hours. You see? It's 10 times. Okay. Depending on the capacity in amps per hour, I charge the batteries faster or slow. Yeah? Right? Okay, this is the battery charger. And what about this? This is what?
Inverter.
What is the difference with the battery charger? In this one, the input is
DC.
DC, positive and negative. And the output is
AC.
hot, neutral, and ground, AC. Oh, nice, no? But this one is more sophisticated, because this one converts this signal into that. Oh, wow. You remember that signal was possible because the rotation of the magnets in front of the coils, no? When each positive and negative pass in front of the coil, one cycle is produced. Okay, with rotation of electromagnets, it's easy to produce AC signal. Where is the rotor and the stator here? Nothing. How they create that signal? It's simulated. Electronically, it's simulated in the circuit board with the computer. For that reason, at the end, the output signal is not a perfect sine wave. It's a little square, a little triangle. It's not perfect. It's simulated. Anybody follow me? For that reason, you see in the label of the battery charger, perfect output signal. It's not perfect. It's, okay. The more expensive the inverter, the best quality of the output signal. Pretty close to the real, but it's not real. They say in the label real signal. It's not real. It's approximated. It's a good approximation. This inverter is for 4 kilowatts, 4,000 watts. And the price of this one, $7,000, $8,000. That. It's a lot of money. Wow. Oh, Mr. Lopez, but in Harbor Free, there are inverters for 4,000 watts, $350. Oh, yeah. Can you bring that inverter and we connect the oscilloscope and we check the output signal of this and the output signal of the other one, $300? the output signal of this is practically a real sine wave. It's pretty similar. It's a little square, but it's pretty close. And this one is a triangle. it's not a sine wave, no? Okay, I have a question. For example, I have an electrical drill or a blower or a fan. Can I connect the fan in the output of this inverter?
Yeah.
Yes, the signal is... Can I connect an electrical drill in the output of this? Okay, in the Mickey Mouse inverter with the triangle signal, can I connect a drill?
Yeah.
Yes, but the drill works at low speed, and in 10 minutes the drill is too hot, and suddenly the batteries are completely drained in the triangle inverter. You understand? That signal is not good. But let me explain. It's not only because the signal is not perfect. This is one reason. The other reason is this. You remember how you calibrate the frequency in a generator? With the RPMs, no?
Yeah.
With the RPMs at the governor, or with the RPMs of the carburetor if it's gasoline, with RPMs, no? More RPMs, more frequency, less RPM, less frequency. It's clear, guys? Okay. This element creates a fictitious simulated AC signal. However, that signal created in the computer, simulated signal, doesn't have frequency, no frequency. It's impossible because it's not created for rotation of magnets in front of a coil. This frequency is also fictitious. I am going to explain how is the technique to convert the DC signal into AC signal. Okay, ready? You bring the brain and the pencil, different colors. Suppose that I have a DC signal, 12 volts or 24 volts. And this is the negative portion of the signal, and this is the positive portion of the signal. I am going to do this. I am going to interrupt the DC signal. I am going to cut it, portions of DC signal, interrupted. This is the step number 1. I am going to cut it, portion of a DC signal. You remember when I explained the procedure to verify if the alternator in your car is working good or not? What was the Lopez technique?
The light.
I put the car in front of a glass, a window, and I check the intensity of the light. You remember? And I accelerate, and I verify if the intensity of the light change. What happened when the intensity of the light change?
Alternator is bad.
It's because the voltage regulator is not good, no? You remember? And you remember that I said that, what happened if I have my car in front of the glass and I see that the light is blinking? This is because in the bridge of diodes, in the rectifier, one diode is broken.
The AC coming through.
Yeah, the AC signal is
Coming through.
is interrupted, no? In portion, in segment. Okay, we are going to do the same. We are going to introduce here transistors and capacitors, transistors and capacitors. With the transistors, I cut it. And with the capacitor, when I cut it, that portion, I storage that portion in the capacitor. No? I cut it and storage. Cut it and storage. And after that, the signal is interrupted. Okay, now I have a DC signal, cut it, segments. And now I am going to do the magic invention. I have a transformer, isolator transformer, a step-up transformer. This is the frame of the transformer. And I am going to pass this cable, the interrupted cable, the interrupted signal, no cable, the interrupted signal into the primary coil of the transformer. Good? okay, what happened in the output of this transformer with the signal?
It's times 10.
Excuse me?
Times 10 power.
What happened with the signal? How is that signal?
It's
The
clean.
output signal will be like this. Because look at this one. And this one here. Yeah, you see? The segments produce that because in the secondary, the second coil received a square signal, but with square interruptions, like this. This is in the output. In the input, you have interrupted positive and interrupted negative. And in the second one, you have that square signal. That's clear? Oh, nice. Now it's square. But what happened, I need rounded that signal to simulate the sine wave. Okay, they install here in these capacitors. This is the project the first project of the next course is this. In the circuit board, we are going to insert the capacitor, the diode, the transformer, and we are going to rectify AC into DC. Here, this is the first laboratory of the next class. And after that, with resistors, and once again, other capacitors, and other resistors. Finally, the output signal here is like this. Is pretty close, It's not a perfect signal, but it's pretty close to the sine wave with those capacitors and resistors, capacitor and resistor after the step-up transformer. Let me explain what is the function of the step-up. If this one have, for example, 100 turns, this one in the output have 1,000 turns. What happens if the input DC interrupted signal is, for example, 24 volts? How much will be the voltage in the output square signal?
240.
Excuse me?
240.
240 volts. And after that, with the capacitors and the resistors, they rounded the signal a little. That's clear? For that reason, if I want in the output hot, and neutral, and ground, 240, hot, how should be the configuration of the batteries? 12 volts or 24?
24.
24, because the transformer is step up. If I want in the output 120, how should be the configuration of the input?
12 volts.
12 volts. If I have three phases, 360 in the output, how should be the configuration of the batteries?
36 volts.
36 volts. Bingo. This is the inverter.